I'll continue in discussing the models that we were talking about last time. Now for definiteness, we'll take one where we have this g of vv here is e to the 2ht. Okay, by the way, in this models, remember we took an affine space, and then we took this vector u and this vector v. Now I'll do the following abusive notation, or if I sort of take the same vector this way over, which should by all rights be called u bar and v bar, I will abuse the notation and call them u and v, because they're sort of like the same thing. Now in which way they're the same thing? Well, in that if I had a curve here like this to this point whose tangent is v, and then I do one of the symmetries here, which remember the main symmetries are the translations, then the point was right here, gets sent to a point over here, the curve gets sent to another curve here, and the tangent to that curve is this vector, which I called before v bar, but as you can see is, v moved over, so to speak. Same story for u, right? I would take a curve this way and then move it over, and the corresponding curve over here, I'll take the tangent and then I'll call those two tangents u, though they should really have different names. One should be u and the other one should be u bar. Okay. Now, that being said, so we have this, g of u is -1, g of v is this, u and v are perpendicular, so this is 0. Now, another language that I haven't defined clearly, because in other words, if this were written in terms of coordinates, then this part here would make perfect sense. But in terms of the formalism that I just described, this is not totally clear. So, so I'm sort of changing language in between, right? But say if you did have coordinates, then we're going to do the following. We're going to take a curve here, and the whole purpose is to basically construct a light-like curve in the space. So gamma of t is equal to b of t comma t. The derivative is b prime comma 1, and I want that g at gamma of t of gamma prime with itself gives me 0. Why? Because that would mean, that the curve gamma is a light-like. Okay, but what is g at gamma t blah blah, gamma prime is this over here. So it's e to the 2ht times b prime squared minus 1, and we want to set that equal to 0, and that would mean that e to the 2ht times b prime squared is equal to 1, and that in turn means that b prime squared is equal to 1 over e to the 2ht, or in other words, e to the minus 2ht. Okay, so b prime is b prime squared, b e to the minus 2ht, so then b prime would be plus or minus this, so it would be the square root, and then b would be plus or minus E T plus a constant. Okay. Now the plus or the minus in front of the e to the ht, that means either this or this. By the way, they should have a minus sign here, so I took the reciprocal of this. Okay, and then now it really looks like that. Okay, so it should really be like this. There ought to be a factor of h in front of the e to the minus ht. I'll let you figure that out when you integrate b. You know, it's probably a 1 over h, blah blah blah, but I'll, you know, somewhere along the line here switch to h being 1 to make our life easier to analyze this. But, you know, hope you can just go through the calculation to make sure everything is fine there. And okay, so that's basically it there. And now I want to show you that for one of these vertical curves, sorry, these vertical lines, right? See, it has two neighboring lines. By the way, I should say that once we do find this light-like curve, by the argument we were was discussing last time, right? Not only have you found light-like curves, but in this two-dimensional example, you found the light-like geodesics. Of course, technically speaking, these would have to be reparametrized, but you basically, you know, at least the curve in space-time, the geometric curve, is already this for the geodesics. But if you want the right parametrization, you'd have to reparametrize these by arc length. But well, in that case, I don't know if I would say arc length, but you have to parametrize them since their arc length is 0. I think you have to reparametrize them now. Alright, so you have this guy here, this guy here, and we already have our geodesics. We know what they look like. There's e to the h curves, and they're asymptotic. So this guy, let's say he receives a signal from these two guys here. Somewhere along the line, these curves have an asymptote. Okay. Like that, and okay, going about this the wrong way. I should say this, that as he's looking at his neighbor, so let's say this is his neighbor right here, as he's looking at this neighbor right here, right, the subsequent geodesics, they'll all be the same one, just translate it over as time passes. And somewhere along the line, there'll be one like this. So you keep shifting them over to the right. What does that mean? That from then on, any other light signal that this guy sends out will not reach him. So in other words, he sees his neighbor for a while, but once he gets to this point right here, he loses contact with that neighbor. And if you're careful, you're going to see that for any other neighbor that's near him, there'll be some time after which he no longer is able to see that neighbor. So he's getting signals before, from him, but once it gets to a certain point here, where that geodesic is asymptotic to him, he'll stop seeing the neighbor. This is the famous losing contact with neighbors, big freeze, etc.